Alright, now let's go ahead and try to understand what is logistic regression. Logistic regression is a statistical model that in its basic form uses a logistic function to model a binary dependent variable. Although many more complex extensions exist, we can actually expand logistic regression to more than two classes classification. So this is the logistic regression logistic regression equation, and this is a logistic function, and it has either the 0, that's the minimum actually, and then the maximum 1. This logistic function can attain a minimum value when t tends to minus infinite. Alright, that's mean at this side, but when t tends to in the positive side, alright, in this positive side, then you will get this one tend to 0, and then finally the whole value of this logistic function will be tending to 1. And in between of these two values, that's mean in between 1 and the 0, it gives the probability of the prediction or the function, you can say. So the many problems require a probability estimate as the output, and logistic regression is an extremely efficient mechanism for calculating the probabilities. So this can be done in the two ways. It can calculate the probabilities as it is. That means it can calculate the probability of the prediction, let's say the 0.6, that's mean the 60%. It can also convert the probability prediction in the classification. So either it can be the 0 and the 1. So if we say that here at 0.5 location, which is the middle one, and let's say the current probability of the prediction is 0.6 and threshold is 0.5, in that case, we will assume that the prediction is 1. Alright, so it can be used for the probability prediction as it is, but with the thresholding, we can also convert it into a binary category classification. Alright, the loss function of a logistic regression actually. So you can understand that although this name is a logistic regression, but this is not the regression function. Alright, so you can but make some correlation between the the loss function of the logistic regression and linear regression, because if you consider this as a linear regression in between somewhere, let's say this value to this value, you can consider it kind of a linear regression, but after this value it is not like a linear regression. Alright, and the error we get in this logistic regression, it is the loss function of logistic regression is log loss actually, and this log loss is defined as here the true value. Alright, 1 minus true value, so this is the true value and this one is the predicted value. Alright, so it's a kind of minus the sum of for all the the data points minus true value multiplied by log of predicted value minus 1 minus the true value into log of 1 minus predicted value. Alright, perfect. So y is actually, you can also consider it as a true value, that is the labeled example at the final output. Alright, since this is the logistic regression, every value must be in between 0 and the 1. So this function will be always positive here, in this case this one. Alright, perfect. The one more thing you should notice here is that since this is a log loss function and this is the loss function, and the main work of a loss function is always try to minimize the error. And if we don't put any barrier on the minimization, then what happens? your loss function always try to minimize the things. And then finally what happens, then it go out of the convergence. So imagine that you assign a unique ID to each example and map each ID to its own feature. Alright. So if you don't specify a regularization function here, the model will become completely overfit, because it's like here fitting a same value to a same value. That's because the model would try to drive loss to 0 on all examples and never get there, and driving the weights for each indicator feature to plus infinity and the minus infinity. So because of that problem, we have here regularization, and there are two types of the regularization, L1 and the L2. Alright, so although we will be having a dedicated lecture for the regularization, but for the sake of this lesson, you can just understand that we try to stop the overfitting by using regularization. Without regularization, a symptotic nature of this logistic regression would keep driving loss toward 0 in high dimensions, and then finally it will explode. Alright, so actually its complexity will be high. That's actually the main reason. So if you have a high complexity model, then this is not good for the machine learning. Alright, so there are two ways in which we can actually stop the overfitting, and those two ways are L2 regularization or L1 regularization. Otherwise, the another way is early stopping, that is limiting the number of training steps or a learning rate. That means that when you start training your algorithm, you should stop at some intermediate layer to avoid any kind of the overfitting. We will be coding all these things in a Python code. Here we have a sample example. We will be using scikit-learn model. We'll be using logistic regression, and this is kind of here a sample example for a logistic regression. And it's really very simple code. We'll be taking here the another lesson in which I'll be explaining you each of these line one by one. If you don't understand it, don't worry about that. We will take another separate lesson on the logistic regression coding. In summary, you can say in the logistic regression that logistic regression models generate probabilities. Log loss is the loss function for logistic regression, and logistic regression is widely used for many machine learning and data scientist practitioners. Alright, so this is all about in this lesson. Thanks a lot for watching it. I'll see you in next lesson.